Okay, so up so far we have been discussing beams in which this support was 100% rigid. Okay? Non-yielding support. Okay? But in real life, the support is also a flexible material. Okay? So what we are considering is, for example, if this is a beam and it is being supported by another beam, okay, through a rigid link. Okay, there's a rigid link connecting these two beams. This is the support beam, and that is the beam we are considering right now. Okay, so let's say this is A and this is B. Then, so you know that the support itself is resting on this beam. This itself is rigid. For the sake of simplicity, we are saying this itself is rigid, but it is resting on something which is flexible. Okay, so this beam itself has some flexibility. Okay, if you push this beam over here, it can deflect. Okay, and it may be compared. Okay, so how do we deal with these problems? The best approach that I understand is, well, what is the action of this rigid link on the beam? A force. Okay, understand? This is x1. And what is the action of this beam on this beam? A force. Okay. And it is equal enough, it is the same magnitude force, x1. This is Newton's third law. Simple enough, I think. Okay. Clear? Isn't it? This beam is supported by this beam and it is providing a reaction x1. Okay. And this beam is pushing the lower beam downward with a force which is the same force as the reaction. Okay. So this is the same force x1, but of course acting on upward on this beam and downward on this beam. Clear? So instead of taking an absolute displacement as our displacement measure, what I mean by that is we're not taking the vertical displacement of just the vertical displacement of B as our displacement measure. Instead, what we are saying, what we take as displacement measure is the relative displacement measure between these two ends of this rigid link. Okay, maybe I can call them C and D. C is that end connected with the upper beam, and D is the end connected with the lower beam. And this itself is rigid; it doesn't deform. Okay, for the sake of simplicity, we have added this rigid link. Okay, now what is the displacement measure? The displacement measure is the relative displacement between C and D. Okay, so even if the load X on this beam, and you see some displacements, the C and D will remain at same distance apart, isn't it? If you apply any load to this, the CD is rigid. So even if this beam is gonna deform, okay, and this beam is also gonna deform, they will have different displacements. We're not talking about those displacements. What we are saying is that this rigid link will now be at somewhere over here, okay. So C and D will still be same distance apart, the length of the rigid link. Getting it? So how do we work with this problem? How do we? So this x1 is our redundant, and the relative displacement between CD is our displacement measure. Okay. So how do we make the problem determinate? We assume that right now you see a connection between these two beams through this rigid link. Okay. So we can make it temporarily determinate by saying that there is no connection between these two beams. Okay, so they are free to displace with respect to each other. Okay, what I mean by that is that you treat them like this. Okay, so the other beam is over here. So this is C and this is D. Okay, this is your primary structure. Getting it? This is your primary structure. Now Okay, you may have any types of loading on it. Maybe it's a UDL. Okay, maybe so there's a UDL. This is your primary structure. Now, just as you in other cases, just as the basic concept says, you have to consider once the primary structure subjected to the applied loading, and then next you have to consider the unit value of redundant. Okay, so in one case you apply this, and then you say, so this is at the midspan. Okay, this beam, this connection is at the midspan. Okay, now this is the primary structure subjected to unit value of redundant. Okay, so the primary structure subjected to the applied loading, which is UDL in this case, and this is the same primary structure subjected to a unit value of the redundant. In both cases, what we are going to do is we are going to find the relative displacement between C and D. Okay, so there are two possibilities. So we're not going to say upward or downward. So there are two possibilities. The C and D will either be coming close to each other or they will be going apart in any case. Okay, if for example in this case, what is going to happen? The C and D, if you apply this load, the C is going to deflect downward. Agree? Okay, the D will remain at the same point because there is nothing applied to it. Okay, we have removed this connection, so the force is not being transferred to this beam. Okay, so this D remains at the same point and C displaces downward. Okay, if this displacement is something called as delta 1, okay, if you have any way to name this displacement, जितने भी उसका magnitude होगा उतने ही amount से ये relative displacement हुई होगी ना, getting it? So if I call it delta 1 naught, delta 1 naught is not, by definition, it is not just the vertical displacement. Okay, it is the relative displacement between C and D. They were this distance apart before the application of the load, and now they are this distance apart. So what is the relative displacement between them? This displacement. Okay, isn't it? Now, next you consider the unit value of the redundant. So what's going to happen? This end is going to displace upward. Okay, and this is going to displace downward. If this displacement is called as delta 1 1, if I can give a few names over here, maybe I could say this is A, B, and if you let me change this for now, I want to give it a different name just to be compatible with the book symbols. I'm just changing this A, B, C, D, and you could say this is E and F. Okay, so this would be E, this would be F. Okay, this is again, I'm sorry, this is, well, so B and E are actually the same things. Maybe okay, let's go with E and F. It's okay, it's fine. Let's go with E and F. Okay, that's fine. Anyways, whatever symbol you use, and at the end of the day, you should end up the same answer. Well, we would call this delta 1 1 as delta 1 1 for this beam. Okay, so this is because of something happening to this beam, and we call this beam as AB. Okay, this beam is called as AB, the cantilever, and there will be some displacement over here. So let's call this as delta 1 1. If this beam is called CD, you will call it delta 1 1 CD. Okay, getting it? So what is the total relative displacement between these 2 points? This goes up, this goes down. So the relative displacement will be equal to this displacement plus this displacement, and they are displacement apart, getting displaced apart. Okay, so I would say, so we need to define a sign convention over here. It's not an upward or downward based sign convention. So displacement is relative, so it's going, so either you take out the displacement apart as positive or the relative displacement together as positive. Let's treat relative displacement apart as positive. Okay, it means this will be negative because this is relative displacement together. They are coming to get close together, and this is relative displacement apart. So this will be taken as positive and this as negative. So I would say I can write down the compatibility equation just as we do in normal way. I can write it down as, you know, let me first write this down. Delta 1 1 would be equal to delta 1 1 AB plus delta 1 1 coming from CD. Okay, clear? And you know this delta 1 naught would be equal to W L raised to power 4 by 8 EI. Okay, and this is together, relative displacement together. And this is relative displacement apart. If you treat this as positive, so this is positive and this is negative. Okay, so what is the compatibility equation now? It will be equal to delta 1. What is delta 1? Relative displacement between C and D, sorry, E and F, the top and bottom of the rigid link, equal to delta 1 naught plus delta 1 1 times x1. In the given beam, this is important to understand, what is the relative displacement between E and F? What is the, in the given beam, what is the relative displacement between E and F? 0. Even after the application of the load, they still remain same distance apart. Although they both displace downward, but the relative displacement remains same, equal to 0. So equal to relative, the distance between them remains same, so the relative displacement is 0. So this is 0. Okay, now you just put the values, delta 1 naught, delta 1 1. Delta 1 1 can be easily found. Delta 1 1 can be written as, for this case you could say it is L cube by delta 1 1 CD, or maybe I can write them down right over here, 1 times L cube over 3 EI. Okay, in a cantilever there's a unit load. Okay, so this is how you get the, so it is L cube over 3 EI. And what about this case? You could work out this part, but we could call it simply, we could simply call it as, we need this displacement due to a unit load. So what could you call it? Flexibility. Okay, so delta CD may be called as the flexibility of this beam under this condition, load and displacement at the same point. Okay, delta CD, and I could say that it is equal to 1 over K CD, reciprocal of stiffness. So I could say delta, so this equation, I mean this equation will be equal to delta, I mean WL raised to 4 over 8 EI plus, so this will come with a negative sign because this is relative displacement together. Okay, plus delta 1 1 is L cube over 3 EI plus 1 over KCD. 1 over KCD is what? KCD, what is delta CD? Flexibility of this beam under these conditions. Load over here and displacement measured right over here. Okay, so this itself is delta CD. Delta 1 1 CD, maybe you could say. Delta 1 1 CD, if you want to say it. Delta C, this is a matter of sample आपने क्या use करना है. So this is, you know, equal to 0. Now you can, if you know KCD, you can solve the problem. Of course, you need to know KCD. Okay, you need to know KCD. Is it clear? You need to write down the expression for X, which you can work out yourself maybe. Or maybe you could simply say, just rearrange this, minus delta 1 naught, okay, minus delta 1 naught over delta 1 1. And delta 1 1 is what? It is equal to L cube over 3 EI plus, either you could write flexibility of this beam or 1 over flexibility, and or you can write 1 over KCD. Sorry? हाँ, find कर सकते हैं, you can find it, you can find it. But what I wanted to say is that if there was a spring over here supporting this beam, and you know the stiffness of this the spring as K spring, or simply K, you could put that value over here, K1 over K spring. We want to keep it, we deliberately want to work in terms of stiffness of the support. Okay? Actually, the support is this beam, but there is just a rigid connection just to make it easy to understand. Otherwise, वो फिर relative displacement आपको समझ नहीं आती. समझ रहे हैं मेरी बात? So I need you to understand the effect of KCD on X value with these two things constant. So what does that mean? If KCD is 0, what will be X1? If KCD is infinity, what will be X1? And what is if it is in between the two values? So these are the two situations. K value, K of the support, maybe I could simply say supporting beam, or simply say any support. Okay? If it is 0, then what is the value of X1? If it is if the K of the support is equal to infinity, then what is the value of X1? If you put 0 over here, it becomes 1 over infinity. Getting it? What does that mean? If K of the support is 0, it means it has 0 stiffness. इसका मतलब ये है ही नहीं. K of the support का practically मतलब है कि ये है ही नहीं. K infinity का मतलब है और बहुत rigid है, 100% rigid है. K of the support equal to 0 का मतलब है ये है ही नहीं. ठीक है? तो अगर ये नहीं होगी सपोर्ट यहाँ पर, तो ये जीरो ही प्रोड्यूस होगा ना फिर. यू कैन कंफर्म इट. यहाँ जीरो पुट कर दें और आंसर देखें. 1 over 0 infinity, anything plus infinity infinity, anything divided by infinity 0. और अगर आप के सी डी को इन्फिनिटी पुट कर दें 1 over infinity 0, तो आंसर क्या बनेगा? डेल्टा 1 नॉट और एल क्यूब और 3i. ऐसा ही आंसर जैसे यहां बनता था कि जब हम इसको 100% रिजिड करें. इसका मतलब ये एक स्पेशल केस था, K of the support infinity. ठीक हो गया? बंद कर.